So let us see the fifth method of speed control, that is EMF injection method. Okay, here, so we are going to inject some EMF into the rotor circuit and we are going to control the speed. So speed control is nothing but we are going to increase the speed or decrease the speed depending upon our requirement. Okay, so using this EMF injection method, we are going to increase and we are going to reduce the speed of the induction motor. So let us see how it is happening. Well, we know that our torque equation under running condition, torque is proportional to slip into rotor EMF whole square by rotor resistance, and we know that our rotor resistance is E2, and this EMF injection is only possible in slip ring induction motor. Okay, so this EMF injection is only possible in slip ring induction motor because squirrel cage induction motor has no terminals to take out of the circuit. Okay, so we can inject some EMF through slip rings into the slip ring induction motor. So how it is going to control the speed of the machine? Let us see. So we know that the frequency of the induced EMF in rotor circuit is slip frequency, that is SF. SF is a slip frequency. So we are going to inject some EMF into the rotor circuit with slip frequency, and it can be injected into the rotor in phase with the induced EMF in the rotor or out of phase with the induced EMF in the rotor. Okay, so that is about EMF injection. Now let us see how the speed is controlled. Okay, we can add EMF. This is EI is nothing but EMF injection, induced EMF or injected EMF. Okay, so if I add this EMF injected to our rotor EMF, that will increase the rotor EMF. Or if I connect if I inject the injected EMF with out of phase with our rotor EMF, that will reduce the overall net EMF. Here you can see in this method of speed control, an EMF EI will be injected into the rotor. That can be in phase with the rotor EMF or out of phase with the rotor EMF. Okay, if it is in phase with the rotor EMF, we can see that our net EMF is sum of our rotor EMF E2 and injected EMF EI. Okay, so this type of control will cause above rated speed control, and if it is out of phase with the rotor EMF, the net EMF will be E2 minus injected EMF, that will be below rated control of speed. So now let us see how it is happening. Here we know that our torque expression is proportional to S into E2 square, as R2 is constant in this method. Okay, here I have to keep the load torque as constant, so I have to make T as constant, and I am going to change the value of E here by injecting EMF in phase or out of phase with the rotor EMF. So if I have to change the EMF, let us say I am going to increase the EMF, our slip should reduce in order to keep that multiplication as constant. That means in order to keep the product as constant, as I am increasing the EMF, our slip has to reduce. Okay, as SE2 square should be constant, the product of SE2 square should be constant. So for example, if I am going to increase the rotor EMF, so for that I am going to add the injected EMF in phase with the EMF, that will increase the net EMF. This is my net EMF, let us say. My net EMF is increased, so in order to keep the torque as constant, our slip will reduce. As slip will reduce, the speed of the induction motor will increase because they are inversely proportional. Okay, this is above rated speed. So by adding my injected EMF in phase with the rotor EMF, I am going to increase the speed of the machine. That is called above rated control of speed. That means I am going to increase the speed of the rotor greater than rated value. This is nothing but above rated control. Now let us see. I am going to add the injected EMF out of phase with the rotor EMF. What is happening? The net EMF will be subtraction of them, that will be net EMF will be reduced. In order to keep the torque as constant, the slip value will increase. As slip will increase, our rotor speed will reduce. Okay, this is nothing but below rated control of speed. Okay, by injecting the EMF in phase with the rotor EMF, I am going to increase the net voltage so that our speed of the machine will increase. Okay, in out of phase control, I am going to add the injected EMF out of phase with the rotor EMF at slip frequency. Both are at slip frequency only. Okay, SF. So the net voltage will reduce. This will increase the slip, which reduces the speed. Okay, this is about EMF injection control, and it can be obtained with above rated control and below rated control, and it is only possible in slip ring induction motor. And the injection of the EMF EI is with the slip frequency SF. Okay, these are the things to remember. Okay, so let us take a problem so that you can understand the concept. So here is the problem based on EMF injection control. Okay, let us see. The synchronous speed is 1000 rpm and rotor EMF E2 is 50 volts per phase, and the rotor speed in the first case is 950 rpm. Okay, now I am going to inject a voltage into the rotor circuit with slip frequency. The value is 10 volts, and that is out of phase with our rotor EMF. Okay, now to maintain the torque as constant, what is the value of rotor speed? So that is the question. So we know the given data is having synchronous speed of 1000 rpm and NR1 equal to 950 rpm. Okay, and E2 has 50 volts per phase, and EI is equal to 10 volts per phase. Okay, and we have to maintain the torque as constant. This is important condition. Okay, in order to maintain the torque as condition, you can see that this is EMF injection control. So torque should be constant, means as torque is proportional to S times E2 square, our S times E2 square should be constant. Okay, so I can write S1 E2 square before adding the injected EMF to S2 E2 plus or minus EI whole square. This is for EMF injection control. This is important. If it is in phase, it will be plus. It is out of phase, it will be minus. So in this case, it is out of phase. So that will be minus. So let us substitute here. S1 can be found out by NS minus NR1 by NS. You are supposed to find the rotor speed. That is possible if you find slip. Okay. The rotor speed will be NR2 will be S times S2 times 1 minus NS times 1 minus S2. If you can find the S2, you have the value of synchronous speed, so that you can find the rotor speed. So we have to find the slip here. Okay, and let us find the first slip. So S1 is 1000 minus 950 by 1000. That will be around 0.05. Okay, so S1 is 0.05 and E2 is 50 volts, EI is 10 volts. Let us substitute the values in them. So S1 is 0.05 into E2 is 50 volts given before injecting the voltage, and S2 is unknown, and E2 is 50 and E1 is 10. It is minus because it is out of phase. Okay, so you can find out the value of S2 here. So that will become S2 equal to 0.07. So NR2 will be 1000 NS into 1 minus S2. This is the thing to be find, NR2, to maintain the torque as constant. So NR2 will become 1000 into 1 minus 0.07. That will become 930 RPM, I think. NR2 is 930 RPM. Okay, so as I have reduced the rotor net EMF from 50 volts to 40 volts, the speed has been reduced from 950 RPM to 930 RPM. So this is below rated operation of EMF injection control. Okay, so this is about EMF injection control. Okay, for in phase operation E2 and EI will be in phase. For out of phase operation E2 and EI will be out of phase. Okay, this is nothing but EMF injection control. So we will be having a last speed control, that is slip recovery method. Okay, in the next class we will be discussing that. Thank you.